and welcome to the Chemistry Academy. In this video we're going to go over reaction kinetics in relation to the Advanced Higher Chemistry course. Now this video is just going to give you a background into the theory behind the kinetics and the equations that we will write as part of writing the rate equation. I'm not going to go over any SQA type exam questions in this video. I will do that in a separate video. So this is just going to give you the background that you need to then be able to understand what to do in the SQA exam questions. So to start off with kinetics, reaction kinetics is just obtaining information on how the rate of reaction can change depending on the concentration of the various reactants within that reaction. So up until advanced higher chemistry, the kinetics of the reactions you do are usually very straightforward, where usually you double the concentration of any of the reactants and the concentration will double. However, that's not the case when you get to advanced higher. The kinetics of the reactions and how the rate changes depending on different concentrations gets a bit more complex. Now, the more complex the kinetics is for a reaction, and by that I mean like if it's not as straightforward as just doubling the concentration of any reactant and doubling the rate, if you get different kinetics for different reactants, then it means that it's unlikely that the reaction's happening in just one straight step. So the more complicated or the higher the order of the reactions we'll talk about, the less likely the reaction is to happen in one step. Now, if we have a look here, this is just a generic reaction where we've got 2 moles of A reacting with 1 mole of B to give you C and D. Now, we've then gone and carried out an experiment and found out that the reaction happens in 2 steps. So if it's happening in 2 steps, it means the kinetics aren't as straightforward because there is a slow step and a fast step. Now, like I said, to determine this number of steps involved in a reaction and therefore the kinetics and the order of it, you have to do an experiment. You can't work out the order of a reaction or the kinetics of a reaction without carrying out an experiment. So that's one thing to remember. This comes up in the multiple choice a lot about which of the following. It's like have one of these random multiple choice questions where you've got 4 statements, and normally one of the statements is that it can only be determined by experiment, or it's something to do with the order of the reaction. That's usually the answer, because if you've got like just a generic equation for a reaction with like an enthalpy change or whatever, that's not enough information to tell the order or anything about the kinetics of the reaction. So you need to have experimental data for this. So you need to have a table of results with, as the concentration of this changes, this is what happens to the rate. So just bear that in mind. But after doing the experiment, we've discovered that 1 mole of A reacts with 1 mole of B to give you this molecule called AB, and then the other molecule of A that was left then reacts with this AB to give you then your products C and D. And we determined this step is slow and this step is fast. Now the slow step is known as the rate determining step. This is the important step that determines the rate of the reaction, because the reaction can only be as fast as its slowest step. So whenever we are then going on to write a rate equation for a reaction, we look at what is involved in the rate determining step. And it's the reactants that we're interested in, because it's the reactants that are allowing the reaction to proceed and then therefore giving us the rate. So when we're writing rate equations, we have our rate equals, and then we have this thing called a rate constant. So the rate constant is just a constant that we can calculate with our experimental data that gives us an indication into how fast the rate is, or what's affecting a factor. It gives us a factor that affects the rate, and that has to be represented as a small k, right? Make sure it doesn't look like a capital K, because if it looks like a capital K, you won't get marks for it. So the rate equations are always rate equals small k times by the concentrations of the reactants involved in the rate determining or the slow step. So because we've got 1 mole of A, we've got the concentration of A times 1 mole of B, which would be the concentration of B. So that would be our rate equation for this reaction here. Okay, we're only interested in the reactants in the slow rate determining step. Because there's 1 mole of each involved, these are essentially to the power of 1. meaning that the reaction is first order with respect to A and first order with respect to B, because the order of a reaction is the power to which the concentration of reactant is raised in the rate equation. So it's essentially telling you how altering the concentration of this substance is going to affect the rate. We'll get onto that in a bit more detail in a minute, but the other way you can think about it when it comes to the generic equations like this, or if you're given in the two steps in the reaction, the order of reaction is also the number of reacting molecules involved in the rate determining step. So because we had 1 mole of A, that's why it's first order. If we had the reaction of the slow step was 2A, giving us an intermediate AA, and then that AA went on to react with B to give us our C and D. So let's say that was the slow step, that was the fast. Oh, can't spell. So the slow step is our rate determining step. So if we were writing a rate equation for this, it would be rate equals small k times the concentration of A, because that's the reactant involved in the rate determining step. But because there's 2 moles of it, we would put it to the power of 2. So this means that there's 2 moles of A involved in the rate determining step. Okay, so, but in terms of if you were asked for a definition of the order of reaction in your chemistry exam, this would be the best thing to regurgitate because it's what's in the SQA documentation. Okay, I think they sometimes accept the number of reacting molecules involved in the rate determining step, but I'm not 100% sure, so yeah, just maybe go with this one just to be on the safe side. But the way it works is the order of the reactant essentially will tell you how much the rate will change if depending on the concentration change for that. Yeah, we'll do that first, then we'll come back to the rate constant thing. So when it comes to the order of the reactions, if you double the concentration of something and you see no change in the rate, that means that changing the concentration of the reactant has 0 effect on the rate, so that would be 0 order. Okay, because changing the concentration is not changing anything. So that would probably be one of the reactants that's involved in the fast step, because it's not determining the rate of the reaction, it's not important. Therefore, anything that's 0 order does not get included in your rate equation. And just like this 1 molecule of A here wasn't included because it's in the fast step. Okay, so anything that's 0 order means it doesn't affect the rate, and therefore it must be in the fast step of the reaction. If then you triple the concentration of a reactant that's 0 order, your rate change is still going to be 0, because as we said, the concentration of that reactant has no effect on the rate of the reaction. If we then double the concentration of something and our rate gets doubled, that means that it's first order with respect to that reactant, because essentially you've taken the concentration change, put it to the power of 1, and then you've ended up with 2. Okay, so that's where this kind of comes in here. That's what you've done to the concentration, what power do you need to raise that to get your rate change. Okay, that's how the order thing works. So if you double the concentration of something and it doubles the rate, then that's essentially you've done 2 to the power of 1, so you get to get your 2, so it's first order. Therefore, if we have a first order reactant that we triple the concentration of, that's like doing 3 to the power of 1. So that means that would give us 3, which means the rate change will end up being timesing by 3, so it will triple. Okay, this is the one you need to watch out for a lot, because people think often that if it's anything more than doubling the concentration, it's more than first order. If the rate's anything more than doubled, it must be more than first order, but you just need to check what's happened to the concentration. That will become more apparent if you will watch my video where I look at some of the SQA exam paper type questions on that. If we then look at doubling the concentration and our rate has ended up quadrupling, then essentially if we take our concentration change, what do we need to put it to the power of to get 4? We need to put it to the power of 2, which means that this must be second order. Okay, this would be this case here. If we double the concentration of A, that's 2 times 2, which gives us 4, so our rate would end up timesing by 4. Therefore, if we have a reactant that's second order and we triple it, that's like doing 3 to the power of 2. So our rate change would actually be 9. So we would find the rate was 9 times faster by tripling that reactant. And then a third order reactant, you don't really see them very often, but that would be like doing 2 to the power of 3, which 2 times 2 times 2 gives you 16. Right? No, 8. Bad maths. So if we doubled the concentration of a third order reactant, we would get a rate change of times 8. Okay, so just remember that the order is whatever power you need to put the concentration to get your rate change. Okay, that's the best way to think about it. So finally, if we finish on the rate constant, so you can often get questions that ask you to calculate the rate constant. In order to do this, you just need to plug in numbers from an experiment. So just pick one of the experiments you're given in the exam and plug all the numbers in, but you do need to rearrange your rate equation to be K equals, and it's usually always K over equals rate over the concentration. So in this case it would be K equals rate over concentration of A times the concentration of B. And then you should in the question have a rate, a concentration of A and a concentration of B, all from the same experiment, and you just plug them all in. For this one, if we were to rearrange it, so we'd write our rate equation, we have then K equals the rate over the concentration of A squared. And just remember to square the concentration, because I always forget to do that. So in these questions, you'll also be asked to write the units for K. Now these are dependent on what the overall order of the reaction is. So the overall order is essentially all the powers added up. So in the overall order of this reaction would be 2, because 1 plus 1. The overall order of this reaction would also be 2, which means that our units for K would be litres per mole per second. So you can memorise this table if you like for the units. So if a reaction's overall 0 order, which you won't really ever see, the units should be moles per litre. If it's overall first order, it'll be per second. If it's overall second order, it'll be litres per mole per second. And if it's overall third order, then it'll be litres squared per mole squared per second. So these are the ones you tend to see more often. You don't really tend to get asked for the rate constant of a 0 order, overall 0 order reaction. Okay, so that's the general introduction into kinetics. The hardest bit people find is usually this bit here, but if you just think about it being the molecules and the number of them that are involved in the rate determining step is what makes up your rate equation, then that usually helps re-simplified a bit. So like I said, if you've got in your slow step, which is the rate determining step, 1 mole of A and 1 mole of B, then that's what goes into your rate equation. If in your slow step you've got 2 moles of A, then that's what goes into your rate equation to the power of 2. So instead of putting the 2 moles there, you raise it as a power. Okay, so I hope that helps. And remember, if you want help with exam questions, then go and check out my other video on that. And if you find this useful, please give it a like. Don't forget to subscribe, and I'll see you again soon.